Good. The part A twice and the part B once was good. You guys didn't struggle with uploading the images to the part B? Worked okay? Awesome. I left a message on some of your tests that if you want to upload one image, you're welcome to. I don't really have that written in any of the directions, but if it saves you time or effort to just take one picture of all of the written responses, you can leave a question blank and just upload one file in one spot. It actually makes it easier for me, but remember those questions get pulled from banks. So I have to have all of those different banks show up in there. But it's not hard for me to download one file and recognize what questions go to what answers you gave me. Do whatever is quickest and easiest for you. That's the end goal. All right, I am, in the spirit of writing a chemistry textbook, which I am probably not going to do, if I were to ever write an organic chemistry textbook, I would title this chapter Regiochemistry and Stereochemistry. Because that's, or not this chapter, this unit, that's what this unit is really all about. So what the heck is that? What is regiochemistry? What is stereochemistry? Is it obvious what's being implied in those words? Structure? Yeah, this has to do with regions of a molecule. Deals with its structure, like that. What else stands out to you about these two words? Is stereochemistry as easy to interpret as regiochemistry? No? So it's this prefix then, right? Saray?
Just from face value and our intuition, it seems to, I guess, connotate
A sound.
but I'm guessing not.
Okay, because why would molecules be interested in sound? Fair enough. Michael?
I was guessing with sound, like stereo, it has different frequencies.
Frequencies. Different what?
Like orientation, slightly different angles, or what is it, mirrored values.
What do you mean by mirrored values? Could you give me an example?
Like rotational symmetries, or like
Right.
things
Okay.
like that.
So you're thinking about frequencies, ways that things are changes, and symmetry. And I think it's kind of interesting that you bring up both symmetry and frequency, because I feel like those are very different things. Symmetry feels like a very physical, visual property, and frequency sounds more like what Saray was talking about with sound, right? Well, I do want you to think about stereo surround sound, but I want you to think of the spatial arrangement. Stereo, we refer to stereo surround sound because of its dimensional implications. Stereo surround sound comes from all around you, all over the place, as opposed to, I don't know what the opposite of stereo is. Mono? Stereo has more to do with spatial arrangement. So you can think of this as geometry. That's one implication of it. Actually, symmetry is another implication, as Michael was saying. We will talk about how symmetry applies to stereochemistry in this unit. So when I say that I would call this unit regio and stereochemistry, what I mean is that in this unit, we're covering the way that the molecule is built, the structure of our molecules, and the way that it takes up space. How is our molecule connected? How does our molecule take up space? That's what we'll be covering in this unit. And that means we're covering a lot of ground. We're going to cover a lot of information in regio and stereochemistry. Here are two of the big regiochemistry things that we'll cover. We're going to start with functional groups. And we're going to talk about nomenclature. These are both big components of regiochemistry. In stereochemistry, we're going to talk about things called conformations. And we're going to talk about chirality. We're going to start with functional groups. Who needs that functional group table that I handed out?
Thank you.
You're welcome. You bet. You're welcome. From your reading, do you know what a functional group is? Or how to define functional group? Chloe.
It's like specific arrangements that you find in a molecule, and when certain atoms are together, they have a different, different properties.
Perfect. It's an arrangement of atoms and bonds that gives rise to specific properties. I think that's a beautiful way of saying it. Sets or arrangements of atoms and bonds that give characteristic properties. A lot of times those properties are reactive in nature. They give different reactive properties, but it can be physical properties as well. Now, there are times where functional groups seem to share sets of atoms and bonds, and they are different enough that they should not be considered the same functional group. I like to break the functional groups into three main classes. I break them down into hydrocarbon first. The hydrocarbon family is the basis for functional groups. In fact, some people don't consider alkane to be a functional group because it is the default set of atoms and bonds. I had a student that sent me this. I'm sorry, it's so blurry. So in this family of hydrocarbons, alkanes are characterized by sp3 carbon-carbon bonds, and of course only hydrogen and carbon. Well, that's the, actually I shouldn't, well, yeah. I maybe shouldn't just say sp3 carbon-carbon bonds, because the simplest alkane, methane, has no carbon-carbon bond. I think maybe it would be better just to say sp3 carbons and hydrogens. The alkene has this distinction by being an sp2 carbon and with a double bond, and the alkyne an sp carbon with a triple bond. And here are the simplest organic molecules that have that functional group. So you guys understand what this fence analogy is telling us? We've got single bonds, double bonds, triple bonds. And I heard from a student before that just made it click. Okay. As soon as we start to put other atoms besides hydrogen and carbon, we introduce our second class of functional groups, what I call the heteroatom groups. In the heteroatom groups, I think it's safe to say we find the largest amount of functional groups. If you downloaded this functional group at the beginning of the semester, this functional group document that was on our class resources page, this is a new version of it. I just updated this like last week or the week before, and it is double the size that it used to be because I've gotten a lot more detailed about things. So I want to point out how certain heteroatom groups are really just derivatives of each other, despite being quite similar to each other. So I want to take the alkyl halides. Notice for a minute that our hydrocarbons all begin with ALK. So when we start talking about alkyl anything, we're talking about being bonded to a carbon group. The YL suffix on alkyl is just saying carbon thing bonded to, and in this case, the alkyl halides. Now this is misleading a little bit because alkyl does generally mean carbon stuff, which is why it's the start of alkane, alkene, alkyne. But when we refer to an alkyl halide, we are referring specifically to an sp3 carbon halogen bond. Because if it's an sp2, there are two different ways that it might show up. It might be a vinyl halide, or it might be an aryl halide. Both are sp2 hybridized, but a part of different functional groups. A vinyl halide connected to an alkene, whereas an aryl halide is connected to our aromatic ring, which makes me remember that I didn't put the aromatic ring. This is our last hydrocarbon. And I want to talk about where I've abbreviated the aromatic ring. I've put this line going through it to R. And you'll notice that the line going through it, it goes through it. It doesn't connect to a specific position. This way of saying that something is bonded to the ring, but I don't necessarily need to say where. I'm just saying that there's something attached. And the R group means exactly that. It just means something. Sometimes we use it to say rest of the molecule. On this document in specific, it usually means some sort of carbon group. But in general, R can often be used to mean a lot of different things. For instance, if I want to say R equals OH versus R equals H, then I get different structures on here. One of them gives me an OH group coming off of my molecule. One of them gives me just hydrogens. Okay. What I've tried to do is clarify all of the different possibilities So I said alkyl halide sp3 carbon to halogen, but then I've got a vicinal dihalide and a geminal dihalide. These are alkyl halides, but they are specific combinations of alkyl halides that we are going to synthesize this semester. So I want you to be thinking about that regiochemistry. Vicinal is describing halides that are in the same vicinity. Geminal is describing halides that are on the same atoms. So this isn't necessarily just under alkyl halides, but in general. Vicinal means the same vicinity. Geminal, anybody here a Gemini? No? It's okay. Oh, you are? Me too, sir. Oh. Okay. Have you heard of a Gemini? You ever met a Gemini? I'm a Gemini. Yeah, That look on Chloe's face said it all. Gemini is the star sign for twins. Cancer is the star sign for crabs, because crab is like, Cancer is crab in Latin. Something strange. So Gemini is the twin star sign, and so when we say geminal dihalide, a geminal diol, we're saying two groups that are attached to the same carbon. They're twins. They're on the same position. So it is not astrology, but it's using the same background as astrology. On the next page, the heteroatoms groups continues, but we introduce our last family, which is the carbonyls. A carbonyl, sometimes pronounced by biologists as carbonyls. A carbonyl is a carbon-oxygen double bond. Specifically, a carbon-oxygen double bond. Now that might sound like the definition of a functional group. It's a set of atoms and bonds. But depending on what else is connected to that carbon, a carbonyl functional group really changes. For instance, if that carbonyl has a hydrogen on one side, then it's an aldehyde. I like to say that that functional group hides at the end of a carbon chain, because you get the carbonyl and then the carbon chain is done. So it's hiding at the side. You can find any sorts of dumb little ways to remember your functional groups, but you've got to know your functional groups. From this point on, whether OChem 1 is the end for you or whether you go to OChem 2 in biochem, know your functional groups. Ketone is different from the aldehyde in that it has no hydrogens attached. It has carbons on either side. I remember the way that I remembered this in college was I thought it kind of looked like a key. But unfortunately, almost every carbonyl looks a little like a key when you abbreviate it, because you just have that carbonyl part. Okay, here's some examples of functional groups sharing sets of atoms but being different functional groups. I want you to consider the carboxylic acid, which has a carbonyl bonded to an OH, which does not have an alcohol. The alcohol has a carbon to oxygen to hydrogen group. You'll notice that we abbreviate alcohol on the first page as just ROH, something bonded to OH. Where is it? All the way at the top. But if that R group is a carbonyl group, then the OH is different. So here's the deal. I have students that will look at a carboxylic acid and they'll say, there's a CO double bond, so there's a carbonyl. Specifically, that carbonyl is carboxylic acid, and there's an OH, so there's an alcohol. they'll say that there are both carboxylic acid and alcohol. And I'm here to tell you, no. You cannot double up on them. The OH of an alcohol has specific reactivity. It has specific properties. And those properties are different than the OH of a carboxylic acid. So if the OH is a carboxylic acid OH, it is not an alcohol. Does that make it clear enough? No alcohol in a carboxylic acid. Here's another example. On the front side, we have an ether. And just above it, we have an epoxide. And the ether is characterized by an oxygen. I love this one. Carbon on ether side. The ether is oxygen with carbon on ether side. The epoxide is oxygen with carbon on either side. But specifically, those carbons are bonded to each other. It looks like an epoxide is a subset of an ether, but actually, it's different. It has different reactivity. It has different properties. So the epoxide shares some overlap with the ether, but the epoxide is not an ether. The ether looks to share some properties with an ester. Oxygen with carbon on either side, but specifically, one of those carbons is a carbonyl. Because of that carbonyl, the oxygen of the ester is not the same as the oxygen of an ether. They have different properties. There are reactions you can run to make ethers. There are reactions you can run to make esters. They are not the same reactions. So when you look at an ester and you try to identify that there is both the ester and the ether, we're looking at that bigger combination. Almost always that's what it is. If there's a bigger group of atoms in arrangement that you can grab for a functional group, you do. You grab the bigger group of atoms. You can see how that's an easy mistake to make, right? We're looking for sets of atoms, and we've got these sets of atoms that repeat in different functional groups. But because they repeat with slight differences, and usually it's that carbonyl, we can distinguish them.
So it's like Boggle.
It's like what?
Boggle.
Tell me what that is.
You know the game with the cues and the letters?
I don't know the game Boggle. Sorry, any?
Maybe that's okay. Anyway,
No, that's okay. This is how I feel up here all the time.
there's like 9 or 16 letters, and each cube has whatever letters on it.
Yeah.
And you shake it, and it lays out, and then you have to find words.
Right.
This reminds me of like you get more points for bigger words, right? So some words are like or, and you're like, oh, it's or it could be like.
That's a good way of saying it.
Bigger word,
Yes.
and you want the bigger word.
You got or, but you could have gotten before.
Right, exactly.
Yeah. Okay, here's another one for you, and use that sheet. Also, I apologize, my printer did me dirty, and it did not do a good job. I'm going to put some functional groups up here. And I want you guys to tell me which are and which are not present. Here's a molecule. I want you to tell me whether those functional groups listed beneath it are or are not present. Take some time, look through your note, look through the sheet.
Sorry, what were the instructions?
which of these 4 functional groups that I wrote beneath it are present? Which are not? Okay. Alkene, present or not? Raise a hand for present. Raise a hand for not. Okay, 3 presents, 1 abstain, the rest, or no, sorry, 3 absent, 1 abstain, the rest present. Aromatic ring, present or not? Okay. Carboxylic acid, present or not? Not present. Epoxide, present or not? Sorry?
Can it be formed if it knocks off that H and then that double bond?
Maybe we could make an epoxide,
But as it is.
but is there an epoxide? No. So, and what you said was if we knock off this H and what?
Could you break one of the pi bonds and bond there?
Like, yeah, actually what we'd probably want is to just get rid of this hydrogen as well and have this. And in theory, it's not impossible, but it is incredibly strained. So I don't know that it would be, if it could form, it wouldn't last for very long. But it's not about what could form, it's more about what is present. Carboxylic acid is out because no carbonyl present, exactly. Epoxide is out because, so what is this oxygen a part of? What functional group is this oxygen in? It's an alcohol. It's specifically an alcohol bonded to an aromatic ring. So it's called an aryl alcohol or a phenol. The PHEN actually refers to the aromatic ring. Okay, now you guys told me that there were both aromatic rings and alkenes, but one of them is just a bigger grouping than the other. If you said there were alkenes, you should have said that there were 3. But to make the aromatic ring, you need 3 alternating double bonds in a 6-membered ring. So this structure does not have an alkene, despite having an alkene kind of shape. All of those carbon-carbon double bonds are necessary to make the aromatic ring. And because each of them is necessary to make the aromatic ring, none of them can stand alone to be an alkene. This OR group is necessary to make the ester, which means that this OR group on its own cannot be a part of an ether as well.
So what kind of geometry do alkenes usually have? Is it never ring-like?
Well, alkenes can be in rings. Yeah, look down at the allylic alkyl halide. Allylic describes a connection next to an alkene. That is the allylic position. So there is an alkene inside of this ring. But if it's 3 alternating double bonds inside of a ring, that's an aromatic ring, not an alkene. And actually in my OChem 2 class this morning, we're starting on aromatics and the differences that they go through in terms of reactions compared to alkenes. They are not alkenes because they have different characteristic properties. That's a good example, right? That's a good way to demonstrate that these functional groups can't stack on top of each other. Okay, with some exception. I'm going to give you a very small molecule, and I want you to tell me what functional groups are in it. 4 atoms. CHOCl. What functional groups are here?
Acid chloride.
Acid chloride is present. It's the carbonyl bonded to chlorine. What else? Carbonyl as I say it, carbonyl is not a functional group. It's like telling me that the aromatic ring is a hydrocarbon. Yes, it is. There's a lot. Which one? So it's not a carbonyl in addition to being an acid halide. It's an acid halide in the carbonyl family. And it has one other functional group.
I would say it's a ketone.
Jacob?
Because the R has to be bonded to a hydrocarbon group.
Good. Ketones have to have carbons on either side. A ketone has to have 2 R groups. And I know we said R can be anything, but on this document, R almost always represents a carbon group. So in this case, R has to be a carbon. The other functional group has to be a carbonyl as well, right? Because the only carbon in this structure is a carbonyl carbon, so the functional groups have to be carbonyl carbons. It has an acid chloride, which we already established.
Is it an aldehyde?
It's also an aldehyde because it has an H bonded to it. That H makes it an aldehyde, and the Cl makes it an acid halide. Okay, one more question.
Also, the Cl being attached to it doesn't affect the carbon, the hydrogen attached to oxygen.
Correct. Now here's an interesting comparison. If we got rid of that H and we made it a carbon group, still an acid halide. It does not become a ketone because a ketone needs carbon on both sides. So it actually cuts back on how many functional groups. This is just acid halide. This is both acid halide and aldehyde.
So you can reuse the double bonded oxygen.
In a very small set.
Yeah.
Generally, that set is like these 1 carbon groups. But yes, in theory, that carbonyl carbon can be used more than once in some instances. Okay, a true or false question for you. Oh, I moved my document. True or false? The structure you see on the screen, ethanoic, propanoic, anhydride, contains an ester. Take some time. I'm going to give you a few seconds. True or false? This structure contains an ester.
True.
Raise your hand for true. Contains an ester. Raise your hand for false. Does not contain an ester. And can I hear an argument from both sides? Who wants to argue for an ester?
I'll detract my vote.
Saray, you want to argue on behalf of there is an ester?
Sure.
Tell me.
Well, there's 2 ester-looking things that are connected to the oxygen, and based off what we can see here, that R is another carbon.
Yeah,
Which is
another carbon chain. Michael?
This is it's not for you, so yeah.
Yeah, against. Let's hear it.
So, you've told us to always vote for like the larger one.
Mm.
This is specifically the acid anhydride, even though it does look like ester on its own on one side and the other side's the same.
Yeah.
Because they're combined with the carbon on either side, it makes them an acid anhydride. It's the larger functional group.
Andrew, do you want to add anything to that?
I would say it's really close, but you don't have the 2 R's. According to the ester, the R has to be a carbon.
Yeah,
So you don't have that second R group for either side.
fair. Okay, so it has an ester kind of shape. Carbonyl bonded to O. It looks like an ester in both directions. Carbonyl bonded to O in both directions. But But the assumption is that when we have an ester, the R group is not a carbonyl. If the R group contains a carbonyl, if there's a carbonyl on either side of the O, that is the anhydride functional group. So the way that Michael said it was brilliant. Look for that bigger functional group. Actually, I think Alvaro was the first one to kind of phrase it that way. Look for that bigger functional group. If you can get something bigger, then don't cut yourself shorter on it. You have to go for the biggest one. Although it looks like an ester from the left, it looks like an ester from the right, the chemistry of this whole group is very different from the chemistry of the ester. Okay, do you guys know The Good Place? You know that TV show, The Good Place? And there's this like autonomous AI being, Janet, who knows all, appears anywhere that you summon her and can give you anything. And Janet falls in love with one of the characters. And Jason's always like, oh, Janet, I love you, girl. And she goes, not a girl. That's how I feel about this. Like, oh, look, it's an ether. Not an ether. Oh, I've got a carboxylic acid and an alcohol. Not an alcohol. Or students will say, I'm looking at the alcohol of the carboxylic acid. Not an alcohol. You're looking at the OH of the carboxylic acid. And I get it, because we will call the OH an alcohol a lot. But the OH of a carboxylic acid is not an alcohol. Looks like an alcohol. I get it. Not an alcohol. And I just love the way, I really hear Janet every time. Every time somebody says something like that, I'm like, not a girl. I get it. I get the confusion, but it's wrong. It's more than that. All right. I want you guys to do a short activity with functional groups. You will be submitting your next analysis on your compound by analyzing functional groups. And I guarantee you at least one of you has functional groups not on this exhaustive table. Okay, but this is exhaustive, but it's not complete. There's a lot of compounds that I did not put in here. A lot of functional groups I did not put in here. A lot of functional groups that I have a hard time even naming because they're so specific and there's so many different versions of ways that it can be combined. So you guys will be applying functional groups to your compounds. What I would like you guys to do is a short activity. I want us to be done in roughly 10 to 15 minutes. What I'm going to do is break you into groups and have you, in your groups, pick a functional group, find a molecule that is somewhat relevant to your life, different than the one that you're analyzing, just by doing a Google search for compounds with that functional group, and then reporting on it, just drawing them up at the front, and telling me what other functional groups are in that same molecule. So to break you into groups, I'd like you guys to line up, if we can, like across the room. You might need to move some chairs. From tallest on my left to shortest on my right. And I'm going to group you guys into pairs. Okay, break. Tallest over here, shortest over here.
Apple people don't do functional groups apparently.
Okay, so let's start with Andrew and Kayla. You guys picked testosterone. How did you go about this first? Did you just Google?
Just Google ketone and found a couple examples.
And I want to point out how you can kind of hear the fact that there's a ketone in the name testosterone. That suffix tells you about the regiochemistry, which is one of the reasons why I'm telling you functional groups and nomenclature are regiochemistry features, because we infer about what's bonded by putting it into the name. You also found an alkene. How did you know that it wasn't an aromatic ring?
Because it only has one double bond, not three.
Exactly. It does not have the characteristic 3 alternating double bonds. And it has a carbonyl on the ring, and the aromatic ring can't have a carbonyl and have all of the bonds it needs, it would break its octet. Great. You also found alkanes and alcohol, and this is where some chemists are divided. Some would say alkane is not a functional group. If it's not something else, then the only thing it can be is alkane. But I would argue alkane is a functional group because it has specific chemistry that is different from carbon groups that don't have heteroatoms. So it's hard to pin down where does the alkane group stop and end. Like for instance, this is an alpha position relative to a ketone. So it has different properties than most alkanes. And these positions are allylic, so they have different properties because of their relationship to the alkene. So it is really hard to say where does alkene start and stop, or where does alkane start and stop. But it is useful to look at it and say, this region is generally alkane-ish. But you'll almost never be marked wrong for not listing alkane as a functional group. Okay, anything you guys wanted to add to that? Great, that was a cool one. We've got Saray and Delaney, and you guys gave us dopamine. You found aryl alcohols, which some people will just refer to as alcohols. But I would say separate to having the aryl alcohol, it does imply that you have the aromatic ring.
Okay.
But we could additionally state the aromatic ring. There is an aromatic ring and there's alcohols. I would say actually there's an aromatic ring and the alcohols are aryl alcohols. I would say that those are useful and separate to say. And then you have this amine. Now you guys might notice on that chart that amines are different than most of the other groups in that there's so many different variations of them. There's a primary amine, a secondary amine, a tertiary amine, and a quaternary ammonium. What are those describing? Primary, secondary, tertiary, quaternary. The number of hydrogens bonded to the nitrogen. So this is a primary amine. How does primary tell us the number of hydrogens? How many hydrogens should be attached? Yeah. I would say it doesn't tell us much about the hydrogens. Would you agree that tertiary and quaternary amines in that list have the same number of hydrogens attached to the nitrogen? So it doesn't tell us about hydrogens. It tells us about carbons bonded to nitrogen. So this is what we call a primary amine because it has one bond to carbon. So we could be more specific. We could say this is an amine. More specifically, it's a primary amine. Now we're going to use that terminology, primary, secondary, tertiary, and quaternary, for some other regiochemistry purposes. And it will still mean bonds to carbon. But the amine is used, it's described differently with those terms than any of the other groups. So we'll highlight that when we come back to it. Michael.
I just have a question for that. So you said that aryl alcohol, that aryl, the first part is what denotes the aromatic ring?
Correct. The aryl is like taking that first part of aromatic and saying it's aryl. The YL tells you a substituent or like grouping off of.
I see. So
It's an alcohol off of an aromatic grouping.
I know you also said phenol or phenyl can be aromatic as well.
Yes.
So would phenyl alcohol be incorrect?
Well, phenyl alcohol would be redundant. So we would say it's phenol. And the OL in there tells you it's an alcohol.
I see.
The phenol at the end of that is telling you the same thing that the OL at the end of alcohol is telling you.
Gotcha. So essentially you're just they're the same thing, you're just determining which part you're abbreviating first.
Yeah. Yes. Delaney.
Since it technically has like two alcohol groups coming off of it, is
Yeah.
it like a stronger alcohol than just like
Not necessarily, although it actually does give it a different name.
okay.
And rather than being called a phenol, it would be called a catechol.
Okay.
there's a rabbit hole. It just keeps going. So if you called these OHs alcohols, I agree. If you call them aryl alcohols, even better. Or phenols, same as aryl alcohols. All right. Eric and Chloe, you guys gave me caffeic acid, which has nothing to do with the caffeine structure. I don't know if you know that. But if you look at a structure of caffeine, it looks nothing like this. But what other functional groups did you find?
Aryl alcohol.
Aryl alcohols. Carboxylic acid, which is, oh, right, you were going for the aromatic ring. Carboxylic acid and then alkene. Right, so having that 6-membered ring with 3 alternating double bonds, that's the aromatic ring, no alkenes in it. But having the carbon-carbons that are off of it create the alkenes. Awesome. Gavin and Liana, you guys gave us a triglyceride. What other functional groups were in it besides your ester?
That's a good question.
And how many esters?
3.
Yeah, there's these 3 units of esters. Whoops, forgot a little 2 in some of these. 3 esters connected. Any other functional groups?
Yeah, isn't the
The long chain.
yeah, doesn't
Alkane. Yeah, because there's no double bonds, there's no triple bonds, so it would be just alkane grouping. Although not all triglycerides are just alkanes. Some triglycerides have these carbon-carbon double bonds, and so they have alkene functionality inside of them. We call that an unsaturated fatty ester, and they can either be trans or cis. We'll talk about what that nomenclature means later in the semester when we get to alkenes. All right, great. For our aldehyde, we've got 2 compounds. I think, Quinn, you drew the one on the top. Do you want to tell us about that one?
Yeah, it's cinnamaldehyde.
Cinnamaldehyde. I wonder where it comes from.
I wonder. Yeah, what makes cinnamon taste like cinnamon or smell like cinnamon?
It is, those of you in lab this semester, you will have the chance to extract cinnamaldehyde. It's an oil. And it does smell like, cinnamon toast crunch. What other functional groups?
An
Alkene,
aromatic ring.
aromatic ring. Do you guys see the similarity between caffeic acid and cinnamaldehyde? The carbonyl is more oxidized. Michael was asking about oxidation. It's more oxidized as a carboxylic acid. It has an extra oxygen bonded to the carbon. And the aromatic ring has this diol feature to it, which means that we could really refer to those 2 compounds as derivatives of each other. We probably could take one and make the other, or potentially do a reverse synthesis between both of them. Okay, Jacob, you drew the other one. What other functional groups did you have?
Alkene.
Just alkene. Now this is where some people might say alkane as well, because they've got these rings. A lot of people will take something like this and say, it's got methyl groups. AI will often give that to you as well. It will say that one of your functional group is methyl. I would disagree. Methyl is not a functional group. Methyl is like a type of alkane, although if it's next to an alkene, that makes it an allylic group. So I would have looked at that and said aldehyde and alkene, done. But Jacob, you have a 6-membered ring with a double bond, so shouldn't you have said aromatic ring?
No,
Why not?
it's not 3 alternating double bonds.
It does not have 3 alternating double bonds. That is the specific character we look for the aromatic ring. All right, Michael, Sammy, and Elvira, you guys gave us hydralazine. Hydralazine. And your functional group was? Where is the hydrazine functional group in hydralazine?
It's the nitrogens going up to the NH2.
Yes. It's the nitrogen-nitrogen double bond is hydrazine. Actually, hydrazine itself is a chemical, H2N, NH2, and it's a really useful fuel for like space travel. I don't know for a fact, but that big rocket that blew up might have burned a bunch of hydrazine. That's a very common fuel. What other functional groups did you find?
Aromatic ring.
Yeah, there's definitely an aromatic ring on the left-hand side. When you get into OChem 2, I'll show that the ring on the right is also aromatic. It's an aromatic ring, but it's not the aromatic ring. But what other functional groups? Anything else?
I guess technically alkenes, if there's not three.
Well, there are 3 double bonds on the left, so
Yeah, but on the right?
on the right, those double bonds are not carbon-carbon double bonds.
Oh, that's right.
So they can't be alkenes. They would be actually closer to what functional group? You have a carbon-nitrogen functional group in your notes. An imine. Yeah, which looks a lot like amine, but instead of an A, it's an I. Not to be confused with amine and amide. Amide has the carbonyl inside of it. All of these nitrogen groups, they really just differ by 1 letter or so. Super easy to tell them apart. I agree, it looks like an imine, but actually the fact that you have a nitrogen-nitrogen single bond will also change the chemistry of how those nitrogens behave. So it's kind of imine character, it's kind of hydrazine character again, or actually, no, a better one would be hydrazone. Do you see hydrazone has a carbon-nitrogen double bond with a nitrogen-nitrogen bond off of it? Where is this? The second page, kind of in the middle, hydrazone on the left. Carbon-nitrogen double bond with a nitrogen-nitrogen single bond. It has more of a hydrazone functionality. You can hear in hydrazone how it resembles hydrazine, but also resembles ketone. Instead of a CO double bond, it's a CN double bond combined with hydrazine NN character. So fun. When I first made this functional group table and it was just one side, it was like everything that I thought was relevant, and it was modeled off of all those functional group tables you can find online. And over the last 3 years now of teaching with that same table, I have found that there are so many different groupings of atoms that you come to recognize throughout the semester, which is why you have this much bigger table. So many are similar, so many are distinct, and it's those small distinctions that can make a big difference. All right, any questions on that activity? How was that?
So when you say know your functional groups, do you mean everything on both of these sheets should be like committed to familiarity?
Yeah, I mean, honestly, some are more important than others. Some are more important than others in OChem 1. By OChem 2, I would want you to have all of these. I actually considered changing that and having a more selective group that is just for OChem 1 as opposed to OChem 2 as well. But I do think that in time, you'll see the similarities. Like allylic halide and allylic alcohol, there's a similarity between those two structures. I forgot to highlight that in red. Whoops. Vinyl halide, benzyl halide, aryl halide, and with benzyl alcohol, aryl alcohol, there's a lot that are kind of repetitive against different heteroatoms. So yeah, I would say try to get to know most of them. The nitrogen groups are more relevant in OChem 2 than in OChem 1, but most of the other groups you'll see at some point this semester. Okay. We're going to move on then to talk about nomenclature. We're going to talk more about how we use terminology, you're welcome, to describe the regiochemistry, to tell us what functional groups we have where and what the structure of our molecule is. Do you guys know what, sorry, do you know what nomenclature means?
Isn't it how you name it?
How you name it? Naming? Thank you. You told me. That doesn't mean that I can remember it. You found what?
I just found the functional group one.
Oh, yeah, yeah.
Can we get one more?
No? Oh. Oh, you wanted the functional groups or the nomenclature?
The nomenclature.
I missed one. Sorry. Nomenclature comes from the Latin naming convention, and I don't know why we don't just call it naming convention. Nomenclature is a bit archaic, but nomenclature is the essence of how we communicate the regiochemistry. Okay, there's actually a few things I want to touch on before. No, I guess there's something I'm going to touch on when we get into the nomenclature a little bit more. So first, let's start off with this idea that a name typically has these components. The name for a molecule has some sort of prefix, which tells you all of the groups that are in the structure but are not indicated by the parent chain. The parent chain is indicated by this root. It tells you how long the carbon is. A locant is a location marker. And you can kind of hear the relation between locant and location. We'll use it to say where along a carbon chain something shows up. And then we have a suffix and what I like to call suffix stoppers. And those can indicate to us hydrocarbon functionality and some other functionality. So a lot of functional groups will show up in the prefix. They are indicated as being part of the molecule somehow in the prefix. The root and suffix tell us about our carbon chain, and then the suffix stopper can inform about a few other functional groups. So let's focus just on the root for now, and we'll start with the parent chain. This parent chain is the longest continuous carbon chain. And I'm going to put in a different color because we will emphasize this as we go throughout the semester. That contains the highest priority functional group. We are going to prioritize our functional groups differently. And we want to get the longest carbon chain that has the highest priority group. The way that we will prioritize, there are so many more functional groups above this, but in OChem 1, our priority list will be alcohols, then alkenes and alkynes tied at the same priority, then any other carbon substituent or halogen substituent. We're going to focus the most on alkyl and halogen groups, and throughout the semester we're going to come back to revisit nomenclature of alkenes and nomenclature of alcohols. Alkenes and alkynes and nomenclature of alcohols. Once you have found the longest continuous carbon chain that contains the highest priority functional group, you give that carbon chain a root. And the root is based, I always forget. I can't remember if it's Greek or Latin. Maybe one of you guys can tell me. If the carbon chain is 1 carbon long, the root is meth. And I know that you guys have heard of things that have this root before. You've heard of methamphetamine. At some point, it has a 1 carbon chain. You've heard of methane, one of our largest contributors to global warming, a potent greenhouse gas, 1 carbon chain. If it's a 2 carbon chain, doesn't it look so silly to just draw a 2 carbon chain like that? We give this the prefix eth. Now we can add a lot of different suffixes onto these prefixes. We can suffix methyl, ethyl, and we can give that YL suffix that tells us a group of, or we can give it methane, methanol, ethene, a lot of different things that come with the suffix, but this is just the root. A 3 carbon chain is prop, and a 4 carbon chain is bute. Now these, in my experience, are the ones that are the least familiar to you, but on the other hand, you've heard them probably your whole lives. You've heard of propane fuel. You've maybe had a grill or a torch that was a propane grill. And butane as well. I go camping with butane stove, 4 carbon chain. So meth, eth, prop, bute, those are the ones people are usually the least familiar with. And then we get into our typical prefixes: pent, hex, hept, oct. All things that you should be relatively familiar with. Now, sometimes our longest continuous carbon chain is not a linear chain. Sometimes the longest carbon chain is a ring. The longest chain never goes between a linear chain and a ring. A parent never crosses linear chain to ring. We'll see that in an example below. But the way that we describe these different rings has to do with the fact that they are cyclic. If the longest chain is 3 carbons in a ring, I can't say prop because it doesn't tell me that those 3 carbons connect all to each other. This is cycloprop. That becomes the root. Cyclobutane. Cyclopentane, cyclopent, cyclohex, cyclohept, cyclooct. We just tap on that prefix and that becomes the new parent, that becomes the new root. So in these molecules below, I want us to find the root. We're not going to piece together the whole name. We're not going to add the prefix. We're not going to talk about locants. We're not going to add a suffix yet. But in the molecules below, I want to show the root, the root for the longest carbon chain. So on the bottom left, what is my longest continuous carbon chain? Just 4 carbons. So this would receive the parent chain bute. We're going to add more things in front because there's more than just those 4 carbons in there. We're going to add things in the end because we want to be specific about what functional groups are in there. What about the next structure? The longest carbon chain is 6. And what is the longest carbon chain? 2 different ways that we could find 6 carbons. So I'm going to show one in green, which gives this group as what we call a substituent coming off of the parent. Or I could start from the top, and I could also find 6, which would give these 2 groups as substituents. Sammy? You could start from the right, yes. And starting from the right, you'd still track these same routes. But you're right.
Okay, you can use either side of that substituent.
Correct, yes. So you could start from the right here and end at the right. You could start from the right here and move to the left.
Okay.
But we've got 2 parent chains that have the same length, but they have differences. They have different number of substituents. When a parent is tied, or when parents are tied, the winner goes to more substituents. So in this case, the way that we numbered it in blue has more substituents. Does that word substituents make sense to you guys? Do you know what word I always confuse it with? Constituents. Like, we're all constituents of our politicians. They are our representatives, we are their constituents. And I always confuse that, but it really is the same idea. These are substituents. They're substituted off of the parent. And we need to look for whichever one has the most of them. If all things else are tied, winner goes to the substituent. All right, now on this next structure, this is where I want to reiterate that the parent chain cannot include carbons from both the ring and the chain. It's either one or the other. So some students will take this and they'll start at the right-hand side of this chain and they'll count into the ring and then around the ring. And they'll find that they can get 8 carbons in a row. But if you are counting a carbon inside the ring, you cannot be counting carbons outside of the ring. A carbon that is in the ring only. So what would be the best, sorry, and I didn't give this before. This hex was the prefix, but specifically, or the root, specifically hex with more groups. What would be the root for this one? Cyclopent. The choices are cyclopent or prop. And this one, pent is longer, so we go with cyclopent. What about the next one? What root should I give it? One more time. Hept. Good. Still have a 5-carbon chain, but this time I have.
So when you describe it, would you say like hept first and then cyclopentane somewhere else?
Anything that is not part of the parent chain shows up in the prefix. So we'll actually call it cyclopentyl heptane. Propyl cyclopentane. So the substituent is always named before the parent. Elvira, did you raise your hand?
I actually think that one is Chex.
I think you're right as well. I
Not
added,
the one you drew. The one you drew is Hept.
the one I drew was hect, but you're right, the one that's on your sheet is hex, yeah? We'll start just off of the ring, yeah? 1, 2, 3, 4, 5, 6. Good catch. What about this last one? What root should I give it? Cyclohex, because the smaller ring will be a substituent off of the bigger ring.
So it would be like cyclopropyl hexane.
Yep. Cyclopropyl cyclohexane. A 3-membered ring coming off of a 6-membered ring. All right, now there are some substituents that are a little weird to name, but they kind of come back to this idea of our roots. And they tie in with the idea of how many carbons are connected at a given point. So to the right, we're talking about degrees of substitution. Now, the way that you should think about this is the number of bonds to carbons. It's a very selective definition. It's maybe not the best, but it will get the job done. First, there are carbons that are not bonded to any other carbons. So a methyl group has no carbon-carbon bonds. And in this molecule that you're given, how many methyl groups, how many methyl carbons do you see? 1. This carbon on the far right is a methyl carbon. Why do we call it methyl? 1 carbon. It's a 1 carbon chain, and that's it. A primary carbon, or you can think of this as first degree, but I don't know why anytime a student tells me, oh, it's a first degree carbon, or like a 1' carbon, it never registers. I call this primary. Primary carbon has 1 carbon-carbon bond. Secondary has 2 carbon-carbon bonds. Tertiary has 3. And quaternary, all of the bonds to a carbon are carbons. So I'd like you to go with that structure and label them all of the carbons as primary, secondary, tertiary, or quaternary. And I would encourage you to label them with these symbols: 1', 2', 3', 4'. Be able to look at a carbon and describe its regiochemistry by how many other carbons it's bonded to. Is that a good oh my god or a bad oh my god?
I thought you meant look at the quaternary one, and I was like, the whole thing, look at the whole thing.
Look at the whole molecule. Label every carbon by its degree of substitution. How many primary carbons? 3 primary carbons. And you know what's silly is we will often call those carbons methyl groups. It's a 1 carbon group bonded to a carbon chain. So it's a methyl group, a primary carbon. It's not a methyl, you see the difference? It's not a methyl carbon, it's a primary carbon, but because of that, Sammy, could you grab the door behind you? Because it's a primary carbon, it's just a group by itself, so it's a 1 carbon group. Methyl carbon, but methyl group. Primary carbon, yeah, methyl carbon, primary carbon. Methyl group. I know. It's not great, but that CH3 is called a methyl group. Okay, what do we call, how many secondary carbons? What do we? 3 secondary carbons. And this, I suspected, would be a little challenging. Here's a secondary carbon. It's bonded to 2 other carbons, as well as here. Oh, no, so you did fall to the challenge. Sorry. There's 4 secondary carbons in this ring. This carbon that's bonded to oxygen still only has 2 bonds to carbon. The CH2 groups we actually call methylene groups. We don't refer to them very often, but in the same way that we'd call CH3 to be a methyl group, we'll refer to these CH2s as methylene groups. How many tertiary carbons? 1 tertiary carbon. And that CH group we refer to as methyne. Although it sounds like alkyne, it's not spelt like alkyne. It's spelt with an I instead of with a Y. And then how many quaternary carbons?
1.
Just 1 down here at that carbon bonded to 4 carbons.
So if the methyl CH3 situation off of the O, if that O was a C, then it would be a 1 prime.
Yes.
Okay.
If this was a methylene group, if this was CH2 instead of O, it would be a primary carbon and not a methyl carbon. Yep. Now we can use this terminology of primary, secondary, tertiary, quaternary to describe a lot of our functional groups. For instance, on your functional group table, which I conveniently closed out of, if you look at that table, you can go through and name all of the different functional groups by their degree of substitution. The allylic alcohol, for example, is attached to a primary carbon, so we call it a primary alcohol. Or with your allylic halide, that's a secondary allylic halide. The halide is attached to a secondary carbon. And this is distinct from the amines. Because when we refer to an amine as primary, secondary, tertiary, we are saying how many carbons is the amine bonded to. As opposed to all of our other functional groups, we say primary, secondary, tertiary to describe the substitution of the carbon that it's connected to. Okay, the way that this feeds into our nomenclature is that we have 2 carbon substituents that are a little strange. We have this 4-carbon chain, and I'm using Y here to abbreviate that it's connected to something. Could be connected to the parent chain. It could be connected to an alcohol. It could be connected to whatever. And if you look at this connection between Y and that 4-carbon chain, Y is connected to what substitution of carbon? A 2', a secondary carbon. So we call this a sec-butyl group. And the sec is describing how the 4-carbon chain is connected. It's a 4-carbon chain connected by a secondary carbon, or it's a 4-carbon group connected by a secondary carbon. Here, the Y is connected to what substitution? A tertiary carbon, and so we call it a tert-butyl group to describe the connection is to a tertiary substituted carbon. Now, one of the confusing parts is that if we take this and we substitute Y as the parent carbon chain, the tertiary carbon is actually quaternary. The tert-butyl group is connected by a quaternary carbon. The sec-butyl group is connected by a tertiary carbon. The methyl group is connected as a primary carbon. So there is this disconnect between what these words mean and exactly how we apply them in the structures. I want you to be aware of that. Okay, we're going to come back tomorrow, and we're going to talk more about our substituents, our locants, our suffixes in the nomenclature. And if we have time tomorrow, tomorrow we will be diving into conformations. So we'll be moving away from regiochemistry into stereochemistry. I'll see some of you guys in lab. Otherwise, I'll see you tomorrow. Enjoy your day.